بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله تعالى وبركاته. Hello dear listeners, it's a pleasure to welcome you today. I will talk in my presentation about dislocation density, stacking faults, and anti-phase probabilities analysis of iron molybdenum phosphor mild powders. And I'm going to talk for about 10 minutes on this subject. The presentation plan contains first study propose, then an introduction about nanomaterial, generalities, and studied system, elaboration and characterization. After that, I present part of my results with our microstructural properties, dislocation density, stacking faults, anti-phase presence probabilities, and in the last, a conclusion. The purpose of this study is determining the phases formed after the milling processes, knowing the changes in the microstructure of powder particles, studying the effect of milling on dislocation density, stacking faults, and anti-phase probabilities. Introduction. Nanomaterials is the class of materials that had internal dimension range between 1 nanometer and 100 nanometer. The small grain size of these materials lead to a behavior that is different from traditional materials of large size and that have interesting properties. Classification of nanomaterials. Zero-dimensional nanostructure. This category includes all materials with a dimension of 100 nanomaterials in diameter. One-dimensional nanostructures. This category is called nanomaterials. The materials such as chips or membranes, such as those used in coating surface for metal products or products by corrosion and others. Two-dimensional nanostructures. In this category of nanomaterials, a scale of 2 dimensions of 100 nanometer is required. Nanotubes and nanotubes such as nanotubes and nanowires, as well as nanotubes, are important models for this class of materials. Three-dimensional nanomaterials. The particle presents 3 nanomaterials such as nanoparticle, metal, powder, and ultramouth ceramic materials, called three-dimensional because of this dimensional on the 3 axes less than 100 nanometers. Terms of nanomaterials: Gorton dots, fullerene, nanoballs, nanoparticles, nanotubes, nanofibers, nanowires, nanocomposites. Properties of nanomaterials: mechanical properties, optical properties, magnetic properties, electrical properties. Application of nanomaterials: energy, transport, army, medicines, electronics, water treatment, space. Nanomaterial manufacturing. Top down. In this way we use bulk materials in the natural state. We are begin getting the materials enter the rich nanotubes, then the nanoscale. One of this way we use to reduce bulk materials to nanowires. Bottom up. In this way we start from the atoms, then separated and assembled to reach the rank of nanotechnology. The method used in the top-down: milling, etching, laser contact method, spattering. The method used in the bottom-up: salt gel, aerosol, chemical vapor disposition. Properties: adding the molybdenum compound to the iron phosphide mixture allows the formation of soft magnetic properties, improving alkaline properties. Iron molybdenum phosphide alloy has many properties: physical, electrochemical. This alloy to be widely used, especially aggression with resistance in white areas. Their alloys can also be prepared at lower loss than corrosion resistance in the other material. Iron phosphor binary complex system. It consists of 4 defined compounds: Fe3p, Fe2p, Fep, Fep4, and different transformations like eutectic and allotropic ones. Iron molybdenum binary complex system, where several transformations take place, as the transformation exists in this diagram is allotropic, monotoctic, monotoctoid, and peritectic transformations. Thus, the iron molybdenum phosphor ternary system equilibrium diagram is a complex too. It consists of 3 defined compounds formed by fusion: MOP, Me3p, Me2p, and there are 2 ferrites. Iron molybdenum phosphor samples were prepared by mixing small amounts of iron phosphors and molybdenum powders. Their samples were prepared inside the glove box in order to avoid the effects of oxygen contamination of the powders inside argon atmosphere. Then the vials were inside rich PM400 planetary made for a high energy mechanical milling process. The milling speed reaches 350 rpm, where every hour it stops for half an hour to avoid everything inside the vials. To know the new properties of the powders after milling with the X-ray diffraction by the Bruker D8 type X-ray diffractometer, simulation with mouse program based off the Rietveld theory. The Rietveld theory, a theoretical method to analyze X-ray diffractograms to adjust the profile of the experimental diffraction diagram, instrument parameters, structural and microstructural. The Rietveld program minimizes by an algorithm based on the least squares method the following function called residue with YCE equal. We now turn to the results. Before the milling process, we note existence of 2 different phases, which are the solid solution alpha and the molybdenum element, and the disappearance of the phosphorus element. After an hour of mechanical milling, we observed the disappearance of the molybdenum compound and the emergence of the iron molybdenum phase with the continued appearance of the alpha iron phosphorus solid solution. After 2 hours of mechanical milling, no new phrases had formed, only the iron molybdenum phase and the solid solution. After 3 hours of continuous mechanical milling to the mixture, no new phrases appeared, but this arrangement different from an hour and 2 hours of grading. The small stable phrases are obtained from 1 to 3 hours of milling, is that iron molybdenum and iron phosphorus solid solution with different structural and microstructural parameters. After 1 hour of mechanical grading, it observed that more intense peak of the solid solution descends a little of return and rises again after 2 and 3 hours of grading. After 3 hours of milling, the grain size decreases for the solid solution and still nearly stable for the iron molybdenum. During the milling, it observed that the proportion decreases slightly of the iron solid solution in the benefit of the iron molybdenum. The change in the dislocation rate is observed in the solid solution, which is the housed and still almost zero for the formed iron molybdenum phase. With our model, we are able to calculate only the SFP of the BCC structure, the solid solution. This parameter reached a maximum value after 2 hours, to return and decline rapidly after 3 hours of milling. The highest values were reached after 2 hours in the solid solution and after 3 hours for the iron molybdenum phase. These parameters increases continually for the formed iron molybdenum phase. Conclusion: the milling of iron molybdenum phosphor in our experimental conditions leads to the formation of iron molybdenum phase in the iron phosphorus solid solution. After 3 hours of milling crystallite of iron molybdenum phase, 17% distributed in alpha iron phosphorus solid solution, 82%. The dislocation density are the highest in the solid solution, with is considered as the host in the solid state reaction during the milling. The formed iron molybdenum phase has the lowest density of dislocation and SFP. The antiphase presence probability increases in the iron molybdenum phase with milling time. Thank you for your attention.